Okay, it's recording now. Go ahead.
Okay, so yeah, we're going to be presenting the fractional programming manifold optimization for reciprocal BD-RIS scattering matrix design. And first, we start with the system model where we have our base station with n transmit antennas, which serves k single antenna users through this R element reciprocal BD-RIS. And for the sake of analyzing the most difficult scenario, aka where we only have the impact of the BD-RIS, we consider that the direct line of sight link between the base station and the users is blocked. This is so that we fix the focus on the impact of the scattering matrix, and then we studied the impact of the beamforming, the transmit beamforming in a different paper. Maybe you can also reference the other paper, maybe just talk about it briefly. So just as a reminder, we can define the scattering matrix that we will be talking about. So we consider the single connected BD-RIS, which has the following constraints um, the that we have the reciprocal, which is the symmetry constraint, and then we have the unitary constraint seen in equation 2, and the symmetry constraint seen in equation 1. So this is the very simplified case where the symmetry constraint is naturally enforced due to due to the way the single connected BDRIS is constructed. This is the simplest case, and this is also just known as a simple diagonal RIS. Then we look at the more um, general case, the group connected BDRIS, which also has the symmetry and the unitary constraint seen in equation 3, which is the symmetry constraint, and in equation 4, the unitary constraint, which also defines the Stiefel manifold. And also, again, now we have the highest complexity case, the fully connected BD-RIS, where also the symmetry and the unitary constraints have to be met. Um, so now we talk a bit about the problem formulation of the uh, problem we're going to be talking about. So we are given a scattering matrix theta and a beam transmit beamforming matrix V, and then we assume that we have perfect channel state information such that an achievable rate of the user k is given um, as seen here, where the SINR at user k is expressed as seen in equation 4. This is a simple scalar SINR expression. As such, we can formulate then our corresponding summary maximization problem, which is now a function of the transmit beamforming matrix and the scattering matrix here under the constraints, under the power constraint 8b and the symmetry and unitary constraint 8c and 8d, where A is just some way we define our single connected, fully connected, and group connected architectures. Um, so once we have defined our problem, we actually fix the beamforming to be yeah, just MMSE beamforming or uniform power allocation, whatever. We fix the beamforming and then focus on the scattering matrix design as we talked about before. So we can just highlight the impact of the scattering matrix on the sum rate. As such, we can formulate our received signal as a vector given in equation 9, where we also have our equivalent channel E. Um, so as such, we can then define our SINR at user K as a function of our equivalent channel and the beamforming matrix. As such, now that optimization problem P2 can be rewritten into the more general form P2A, where we now focus on the group connected BD-RIS architecture, which is the more generalized architecture, and then therefore we can provide a solution for the fully connected, group connected, and the single connected just by changing the number of groups we have in the BD-RIS. As such, for simplicity, we can rewrite our sum rate as eta, which is the sum over all k's users, eta k, which is the rate at user k, and as such, we can now formulate optimization problem as seen in P3, where we now move the symmetry constraint into the objective function with this term based on the Frobenius norm, which tell us how far the scattering matrix actually is from being symmetric, and we can find a solution for this problem. So to that extent, there are some steps we can take to actually even simplify this problem, because the sum rate is highly non-convex. As such, we can use standard fractional programming tools to convexize the objective function, and we can start doing this by uh, applying the Lagrangian dual transform to the rate objective, and we get this equivalent problem as seen in equation 15, where now this tau k is auxiliary variable added for the Lagrangian is a Lagrangian dual transform auxiliary variable, and it's equal to the the SINR we have defined before. Um, Accordingly, then we apply the quadratic transform to the equation 15, and then we obtain the fully convexized version of our objective function, which is seen now equation 16, with again the quadratic auxiliary variable yk as defined in equation 17. So having now defined our convex convexized version of the objective function or the sum rate, we can define a convex optimization problem P3 as seen. We can define a convex version of the optimization problem P3 as seen in P3a, where we now have a convex objective function and a manifold constraint. So to this extent, we can use the conjugate gradient ascent method, as will be defined further, but to this extent we are going to need to define the gradient of the objective function as seen in equation 19 here. So for simplicity, we provide the closed form gradient of the objective function, which with respect to each group, and this is seen here in equation 20. In the paper, actually, we also provide um, the scenario where we just use a fixed uniform power allocation beamformer. So then we will not have beamforming vectors here, but we will instead have just some scalar values. And that equation can be seen in the paper. For simplicity, we provide here the most general version where we just considered MMSE beamforming. Yeah, afterwards, we just follow the conjugate gradient ascent as will be explained in the follow-up. And at the end, we um, obtain the final scattering matrix through a projection method, which was proposed by Fang et al. In this paper that we have referenced here. So this is due to the fact that actually our penalty-based method is not an exact um, constraint. It doesn't fulfill the constraint fully. So that's why we need, in order to get a reciprocal beyond diagonal RIS, which is also lossless, we need to again project it at the end. Um, so to dive more deep into the algorithm, we have derived we have provided the full algorithmic steps here. So in the beginning we just input our equivalent channel or the transmit channel matrix, the receive channel matrix, the mac the power budget, the number of users, and the power density we have, and the number of groups, of course. And in the end, we obtain an optimized RIS matrix. So in the beginning, we initialize our scattering matrix as a random block diagonal unitary and symmetric matrix. Accordingly, we then compute the initial FP, the fractional program auxiliary variables, tau k and yk for all of the k users. And then we compute our initial objective, which is now the convexized objective for this randomized theta that we have, and then we compute the remaining gradient R0, which is just a tangential projection. And so here we have, again, as a reminder, how we have now defined our objective function. And here is the formula we use for the tangential projection, which is based on the gradient of the objective function and the theta itself, then the point we have at the manifold. Um, Accordingly, we then set the initial search direction, which is this psi, and then for each iteration, so from starting from the 0th to the ith CGA iteration, we then we check if this direction is valid with this if clause from line 5 to 7, and then we compute the step size. So this alpha I is a step size, which is done using the Armijo line search, and then we update the theta according to this step size. And it's important to note that actually this is where one part of the manifold optimization step is done. This is also the retraction method. So accordingly to this step size and the direction and the theta itself that we have updated, we can then retract it back onto the manifold. And yeah, we have a solution which lies on the manifold. Uh, Afterwards, we can then compute the new FP variables tau k and the yk, which are computed with the new updated uh, scattering matrix. And we compute the new objective, the new gradient, and this B is called the CGA momentum term, and it's defined as here seen in equation 12. Accordingly, we can then update the direction psi using our previous direction, the new remaining gradient, and the CGA momentum term. And then we have um, some convergence criterion, and if it's met, then with this tolerance eta, then the loop breaks, and we are now outside of the CGA. So our CGA algorithm has come to a stationary point, which is usually a local minimum. And afterwards, as we mentioned beforehand, for all of the groups, we extract each group from the final matrix that we get from the final scattering matrix, and then we symmetrize each group. We then also uh, project it. So this symmetrizing, we project it onto the set of symmetric matrices, and then in order to get the unitary matrix, we need to perform the SVD on the symmetric matrix, and then use the left and right um, unitary matrices to get the final projected unitary symmetric matrix. And as such, as we have done this unitary and symmetric projection on all the groups, we then assemble all of the groups into a block diagonal matrix, and then we get the fully optimized theta in the end. So a bit about the simulation setup. We consider IID fading channels, and that our system is operating at 2.4 gigahertz with a noise power density of minus 80 dBm. Uh, More about the path loss model, we consider this distance dependent path loss model where we have our C0, which is just some reference path loss at reference distance of 1 meter. So this D0 is the reference distance, and this rho factor is a path loss exponent. And then we consider that the base station is 50 meters away uh, uh, from um, the BDRIS. And accordingly, the state-of-the-art benchmarks are as seen here, reference 2 and 3, and we will go a bit into the results that we have provided in this paper. So first of all, we provide results for summary performance, where we compare our proposed scattering matrix with fixed MMSE beamforming and our proposed scattering matrix with uniform power allocation against both references, where we can see that we obtain higher for a relatively large transmit power, we obtain better summary performance. And following, we then provide results for um, sum rate performance again, but as a CDF for all of the different architectures that we have considered. So this is just our proposed scattering matrix following algorithm 1 in combination with uniform power allocation, and for all of the different um, architectures that we have considered, namely the single group connected with group size 2 and 4 and the fully connected architecture. And in the end, we have the summary performance as a function of the number of reflective elements R, as we can see that we outperform the state-of-the-art listed here in all of the considered architectures, where most notably we can see that the single connected architecture even beats the group connected architecture with a group size of 2 from the state of the art that we have considered. So yeah, this is it for the presentation, and thank you for your attention. Any questions?
Thank you, Marco. I have a couple of simple questions. Please don't stop showing.
Yes.
So the first thing is that, so here the gain is relatively small. Can you explain why the gain here is relatively small? This is the fully connected case, or which one is
It's
this?
a single
Oh,
connected.
it's a single
I mean
connected. Okay,
here,
so let's go ahead.
yeah. So here we consider a pretty sparse setting. So we only have two users and two transmit antennas overall. So the gains are mainly gonna come from the scattering matrix because the beamforming doesn't really play much of an effect here. As we can see here, the MMSC and the uniform power allocation receive almost the same sum rate performance. So the main thing to notice here is that our gains just come from the scattering matrix. And yeah, I mean,
Yeah, but then a couple of slides down, you show that for the single connected, you have a significantly one more slide down. Yeah. So what is the difference between this simulation setup and the previous simulation? Where here we see a much more significant gain of the proposed
yeah,
method. Yeah. Can you
so
explain the difference?
yeah, so here we have actually five users and five transmit antennas, and we only take the value at 20 dBm. So our most noticeable gain is at 20 dBm. So if we just explode the system a bit more, then we can notice that um, we get certain gains from that as well.
Okay, so you're saying that as you scale the system up, your gains at high SNRs, or is this not XNR? This is transmit power, right?
Yeah, yeah, sorry, yeah.
Reflective elements. Uh, yeah. So at higher system size, so higher, larger number of users and number of antennas,
Hmm.
and at a higher transmit power is where the gains are most noticeable. Correct?
Yes, yes.
Okay. Very good. Now, can you go back one slide? So
Here?
here, what are we? Yes, what are we seeing here? We are seeing the relative gain in terms of some rate as you grow from single connected to group
Fully
connect. So the question is here, yeah, question here is why don't you show also here the results for the state of the art system?
Yeah, I had it, but I had the results for that, but I think there was something wrong with the state of the art. And I mean, we've shown previously that we outperform it, so it shouldn't change. It was just cluttering the figure, I believe that's why. It
Okay,
was very far behind, so
I was very far behind. Okay, all right,
yeah.
good. Now one question just for the sake of the audience. I'm sure people might ask that.
Mm.
And with that goes also a suggestion for some slight improvement. If you go back to the formulation of the problem where you move one of the constraints to the as a regularization term, you have, of course, your regularization parameter new here. So how do
Yeah.
you optimize this new? Can you say some words about it?
Yeah, I mean, we have just chosen it empirically, and then it's very common in such formalizations just to choose it empirically. If you choose a too high of a value, then you get numerical instability. If you choose a too low of a value, you also get the same. It doesn't really matter if you choose too much of a value, it doesn't impact actually the objective function. So you can choose it empirically as long as it's not too high or too low. And of course, if you do a full sensitivity um, um, analysis, you might get a better objective value at the end, but this was not the goal of the paper itself. We just did this to show that actually, even with an empirically chosen value, we can outperform state of the art, as we have shown in the simulation results. So of course
Right.
you can,
But
yeah, you can
but
optimize
from
this,
what
but
sure, but from your answer, one can also infer that the gains could be higher, right? Because what you're saying actually is that you didn't perfectly optimize this parameter. You just took a empirical value and that works. But
yeah,
it was not optimized. But in principle, it can be optimized even for different transmit powers, different group connectivities, and all of that. And therefore, the
yes,
currently shown gains can only be better.
yes,
Right? Okay. All right. Thanks for that. I'll stop the recording now.
yeah. Actually, maybe here because it's actually I only have the value for distance from the BD-RIS to the from the base station to the BD-RIS. Let me check actually the journal paper. Maybe I also should have the distance from the base station. I mean from the BD-RIS to the user. Second. Yes. So I should add here that the distance from the BD-RIS from the base station to the BD-RIS of 50 and 2 point from the BD-RIS to the user.
Okay. You're just talking about some missing. Okay, I'll stop the recording.
Yes.